thanks also for inviting. Okay, and thanks also for inviting me to Caltech. So it's a pleasure. I've never spoken at this time of the day, but then there are mishaps when people do things at the time of circadian law. So just forgive me if I don't get something right. All right, so let me get started. All right, so I work primarily in the areas of aeronautics, on robotic motion planning, and I started working on infinite dimensional systems while I was still a PhD student with Sunjo. And then since then, I've been working on and off in this area. This area, I mean, it's really very exciting and also hopefully very promising. So I thought I would share with you some of the work that we've done in this area, which serves to highlight some features that are very unique to infinite dimensional systems. So I'm going to start by talking about some of the earliest work that Sunjo and I did on PD systems with finite relative degree. I'll just give you like literally a very, very brief background then to general infinite dimensional systems. So I assume there's some grad students here in the audience. In case you haven't seen these things before, just a quick introduction to get you started. I'll then talk about a control framework that we started developing a few years ago. We call it a dyadic adaptive control framework. We've introduced a few extra elements in the mix, especially we've tried to introduce LQR in it, try and see whether we can get some guarantees on suboptimality. And some of the recent results that we got on that framework while dealing with what are called as non-coercive Lyapunov functions. These things are extremely unique, if you will, to infinite dimensional systems. So we'll just get started on that. All right. So my core interest has always been in aeronautics, in flight mechanics, in flight control, and at some point we started talking about looking at controlling airplanes with flexible wings. So as you know, airplane wings have been getting flexible over the years. So one of the things I learned from a prof at Illinois was the DC-3 was probably the last airplane with strictly rigid wings. And since then, they've been getting more and more flexible by the decade or by the year. So these wings are lighter, arguably, depending on how they're designed, they can give you better control authority. And another feature that is being touted is that they give you better gust ejection. Now, all of these good properties come at the expense of a higher susceptibility to wing flutter. Now, at least commercial airplane wings are typically designed to be flutter resilient across the entire envelope. And some fringe parts of the envelope have to be expanded to take into account such maneuvers as dives at high altitude. Now, some modern airplanes have had problems in those fringe areas of the flight envelope, as a result of which they've been using flight control loss to close the loop and actually stabilize the wing. So for example, it's well known that the Boeing 747-8 Intercontinental, experienced flutter problems very early on in the flight tests when all of this was being done in the open loop during a dive at 30,000 feet. And that was the first case that we are aware of where an active control modification was made through a software to solve the flutter problem, and it was subsequently certified by both the FAA and EASA. There's a similar a vibration damping system, on some of the heavier variants of the 787 as well. So we've moved from designing wings to be flutter resilient by design in the open loop to now accepting, at least in some parts of the envelope, cases where the wings can flutter in the open loop or they can show some undesirable behavior, but these can now be stabilized in the closed loop, and these designs are now acceptable and certified. So how do you control wing deformation, or how do you control wing flutter? So there are two ways to do it. In fact, both of these have been used at some point of time or the other. The first is to use passive attachments or loads at the wingtip for energy absorption. Some airplanes also use, they leave like some residual amount of fuel in the outboard area of the wing to play the same role. The approach that we are interested in is where you do it using either ailerons or elevons, as the case may be, and use an active control law to suppress flutter. So the suppression system, if you're interested in looking up, it's called as the outboard aileron modal suppression system. And this is the one that's used on the 7478 intercontinental. So this is how we started looking at the sort of how we got into infinite dimensional systems in the first place. So let's take a closer look at Flutter. So if you look at a very simple textbook example, you will know that a wing can be modeled as a beam with 2 degrees of freedom. There is torsion and then there is transverse bending. Now, these two modes show a fairly substantial timescale separation in that the natural frequencies are sufficiently well separated from each other. So an example is shown here in subfigure A, where you see the modal frequency normalized omega by omega naught on the y-axis as a function of the normalized flight speed on the x-axis. So when the flight speed is 0, you see that the two frequencies are separated by a ratio of about 2.5 in this fairly simple illustration. And as the speed increases, these frequencies start to merge. And thereafter, at some point, one of the frequencies goes to 0, and this is where you get divergence. And somewhere before this point, you get the onset of Flutter. So one of the ideas that we had at that point was, well, if Flutter happens sometime before divergence, and it's primarily like a resonance phenomenon between these two modes, what happens if we were to artificially increase this separation in the frequencies? So leave bending alone, for example, just increase the separation between torsion and bending. So basically increase the torsion frequency. Would that enable us to increase the Flutter speed in some way? So this was a hypothesis, and that's what got us started. So to get into the math, let's start with a very simple second order wave equation with Kelvin void damping. This represents the torsion dynamics in isolation. So you have the wave equation here in the first line. We've added Kelvin void damping to it. And on the right-hand side, you have aerodynamic forcing. And it typically, as long as you are in the linear regime, it's only proportional to the incidence angle theta. So this sits on top of the angle of attack. Now, the wing is clamped at the root, so there is no deflection at the root. At the wingtip, we assume that we can give some kind of a control moment. And this comes from the deflection of the aileron or any other surface at the wingtip. Now, when you look at this control problem, your first instinct is, well, how do you model wing vibration? Well, when the wing starts to vibrate, one of the things that happens is obviously the lift starts to show an oscillatory profile. So what we say is, all right, let's not worry about controlling vibrations per se. Let's just worry about ensuring that the lift tracks a certain desired profile. Now, in a very abstract way, lift can be thought of as just the integral of theta, which is the incidence angle over the entire wing. So all we want to do now is to make sure that this particular term, the integral of theta over the wing, tracks some signal h of t, which is some reference signal that you as a user get to create. And depending on what kind of tracking you're interested in, you might want to guarantee asymptotic tracking, which is why we just add this limit constraint. So that becomes our tracking objective. And hopefully, if we were to achieve this, we might also be able to achieve some form of stabilization. All right. So let's just see how this works out, because now the thing that you have to bear in mind is you have a system with a lot of dimensions, because the system is infinite dimensional. It's a partial differential equation. And in that objective that we created, we are controlling just one variable, a single dimension, if you will. So we'll start with some simplified notation for the wave equation. We write it as so. And just to keep things a bit simple for the purpose of this derivation, we'll also assume that this coefficient m of x, which basically reflects the lift distribution on the wing, is a constant. In fact, even if it's not a constant, it's fine. Most of this derivation really just goes through. All right. Now, you would also know probably from courses that you've taken in aeroelasticity that the criterion for this wing to be stable in the open loop, that is with the control input u set to 0, is that this ratio m by a be less than pi square by 4l square. This is a standard open loop stability condition. And when these two terms are equal, you get wing divergence, and somewhere before divergence, you have Flutter onset. So let's look at a tracking error now. So we define the tracking error as the integral of theta minus some reference signal h. And here something interesting happens. When you differentiate E twice with respect to time, you recover the control input U on the right-hand side, plus a couple of other terms. H is a reference signal, so the terms in H are known. M into E is the tracking error again. And you end up with these two terms, which arise from the strain at the wing root. And these are terms that can, at least in principle, be measured. So I have a control signal here, which can in principle cancel out all of the undesirable terms just to the right of it, and leave us with some very nice looking dynamics of the form shown here. So this is a second order dynamics in the error, and this decays to zero exponentially fast. And in fact, this works even if the signal h of t is time varying. So this is a nice property. So what we've been able to show here is that you can design U and drive E to zero. Now, as I warned you a while ago, this only is one dimension from an infinitum. And in control, it's well known that this kind of output feedback, if you will, does not guarantee that the system is stable as a whole. So it turns out, however, that because this is a PDE, this particular condition plays on at the boundary of the PDE and actually creates the right sort of conditions for stabilization. So to see that, we'll just introduce a new variable called W, which is the integral of theta over a part of the wing. So this could be W of X, if you will. So that it's integrated over the outboard portion of the wing. And let's look at the case where H is zero. So you are just trying to suppress any excess lift that comes on in addition to what alpha is generating. And with this assumption, your PDE for W now looks like so. It looks like the classic wave equation, put up by a few extra terms on the right-hand side. And you have these three boundary conditions, two of which look like a clamp on W and one which corresponds to a strain condition on W. Now, I must add here that this representation is one way to look at the problem. You can alternately think of the same condition as the original PDE with an additional boundary condition added as an integral term. Now, here's what happens as a result. In the original open loop system, the open loop eigenvalues are odd multiples of pi by 2. And in fact, this pi by 2L is what gives rise to the divergence speed condition. If instead of a wing which was just clamped at one end, the wing were to be clamped at both ends, the smallest eigenvalue would go from pi by 2 to pi, and then thereafter every multiple of pi would figure in there. Because of the way the extra boundary condition gets added here, together with these additional terms on the right-hand side for the dynamics of W, it turns out that the smallest eigenvalue in the closed loop is actually 2 pi, and then you have subsequent even multiples of pi. So in effect, the first eigenvalue has gone from an open loop of, the open loop value of pi by 2 to a value of 2 pi in the closed loop just by this particular output feedback. And that's actually what happens. This eigenvalue is proportional to the frequency of the torsion bending mode. And when this eigenvalue goes up by a factor of 4, it immediately impacts the divergence speed and the flutter speed. And then you get a curve that's shown out here schematically as this pink curve in the closed loop. So in principle, it means your divergence dynamic pressure could go up by a factor of 16, but typically flutter happens at high Mach numbers, so it may not translate into an increase of the speed by a factor of 4. It would typically be a smaller factor, but you've managed to push the flutter envelope forward. So this was I think a pretty interesting result. It was obtained on a fairly simple example, but what it served to illustrate was that PDs really do have some special properties that depart from finite orders, from finite dimensional systems, and there is a possibility that these properties can be put to good use for control. All right, but as it happens, that only is the starting point for everything else that has to come after that. So most of you would be familiar with the Helios accident that happened several years ago, must be the early 2000s now. And the Helios was this nice high aspect ratio wing propelled by a whole bunch of propellers that you see out here. And this plane broke up at altitude when it encountered encountered some turbulence. What is interesting is that this breakup happened because turbulence actually excited a sort of a resonant mode in the dynamics, and that resonant mode featured both the structure as well as the rigid body dynamics, and that's what I've just sort of highlighted that here. And what it went on to show was the role that can be played by the interaction of the structural dynamics and the rigid body dynamics in destabilizing the airplane and even possibly causing some sort of a catastrophic failure like this. So just to give you an idea, if you look at the rigid body modes, you would be familiar with this. The fast modes typically have a time constant of the order of 0.1 seconds. That's roll. That's maybe a bit too fast for most wings, except at extremely low speeds. Then you have the relatively faster modes, in the short period and touch roll, with the time constant on the order of about 1 second. And these time constants are actually close to the time constants of moderate aspect ratio wings. And the slower modes like fugoid or spiral are close to the time constants that you would see in a very large aspect ratio wing. So this is the kind of coupling that you have to look out for. In the case of Helios, however, this airplane design was a bit unconventional in the sense that there was no horizontal tail, and that probably slowed down the pitch mode. And therefore, instead of the fugoid interacting with such a large aspect ratio wing, it was the pitch mode that interacted with it and led to this kind of a catastrophic failure. So the message is that when you look at flexible airplanes, it makes sense to look at the wing flexibility, the structural dynamics of that wing, and the flight dynamics jointly. And it was this motivation that really got us looking into infinite dimensional systems, because after a point when you do control design, you look for guarantees, you look for methods that can give you some sort of optimality, some kind of nice mathematically elegant control designs. And that's how we got started working on infinite dimensional systems. So the idea of infinite dimensional systems, the phrase, if you will, just so that we are all on the same page now, it comes from the fact that the dynamics of a PDE evolve on a functional space. So the rigid body dynamics, in contrast, are described only by 8 states. On the other hand, waves, the Euler-Bernoulli beam that describes the bending motion, the dynamics of a fluid, for example, or transport phenomena or heat transfer, all of these are described by partial differential equations, and their solutions are functions. So that's the point that's the place where the name infinite dimensional systems comes from. Now, typically, we deal with systems involving PDEs by ODE approximation. So we use a Galerkin approximation or something similar to construct a set of ODEs, which can then be put together with other rigid body equations of motion and controlled as a whole. The trouble is these models have extremely large orders. So for a typical wing, for example, to describe the dynamics accurately, you need anywhere from 50 to 100 modes. I'm sorry, about 50 modes, so gives rise to about 100 equations, given that these are second order dynamics. So these equations are, these systems are fairly large. And the other thing is, as I just showed you a few minutes ago, PDs do have some special properties that can be exploited. So the question is, can we do something worthwhile with the PDs themselves instead of just breaking them down into differential equations and working with systems of large order? So that's the problem that we started getting into. And as it happens now, there is a lot of math. I mean, control theory is anyway fairly rich mathematically. And that's even more so with infinite dimensional systems, because the math can be a bit heavy for someone with an engineering background like me and not with a proper mathematics background. But it's interesting nevertheless, and that's where a lot of the learning really takes place. So let's just look at how these equations are represented. So let's start with the simple wave equation. We'll assume for the moment that there's just one dimension. The spatial dimension is capped between 0 and 1, no boundary conditions. And let's look at the undamped wave equation that's shown out here. Now, you can represent this equation as shown here in the second equation. So we define this variable z, or z, as w, and wt is the first derivative with respect to time. And with this definition, you can write z dot as a into z, where a is this particular matrix. Now, unlike traditional matrices in finite dimensional systems, this matrix A doesn't consist of just numbers, it consists of operators. So for example, this term A naught differentiates W twice with respect to the spatial dimension. So this is called as the operator representation of the system. Now, one may ask, well, where are the boundary conditions now? Because you don't see them written anyway in here. So it turns out that the boundary conditions are actually captured in the definition of the domain of A. So remember, these operators act on functions because the system evolves on a functional space. So the question is, what kind of functions does would you allow the operator to operate on? And that's where the boundary conditions come in. So they are buried here in the domain of A naught in this particular case. Now, this representation, z dot equals az, is comparable to what we see in finite dimensional systems. So it raises a very interesting question, which is, if the representations look alike, can the representations of control signals of our typical stability calculations also look the same? And if they look the same, then we can extend what we know from finite dimensional systems. We know all of this very well. We can extend it as is to infinite dimensional systems. So just to tell you how closely these two things are related, let's look at a simple finite dimensional system, x dot equals ax plus bu. Here x evolves on some n-dimensional real space. You know that the solutions of this particular system are written in terms of this semigroup exponent of at. That's well known. And then if this term bu is non-trivial, then you get a solution that looks like so. So you have the exponent and the convolution featuring the exponent and b. It turns out that even in the infinite dimensional setting, these definitions actually carry over, of course, with a few caveats, because you're going now from a finite dimensional system to a functional space. So we define for this abstract infinite dimensional system, this object T of T. It's called as a C naught semigroup. Don't worry about the technicalities, but the key point is, with this semigroup T of T, you can write the solution of the unperturbed system much as you would in the finite dimensional case. So we write Z of T equals T of T into Z0. So it's unperturbed for now. And the definition of A, which is this abstract A that you saw here, the matrix in this system, if you will, it actually comes about as a result of this particular limit. So you look at T of T and allow that T to collapse to 0, and this gives rise to this term A. You can actually check that this definition also works in the finite dimensional systems, except out there, the exponent of AT makes a lot of intuitive sense, visually, if you will. That doesn't happen with T of T. Other, it doesn't happen with A. So you don't, so e raised to AT with this infinitesimal generator A doesn't make a lot of sense visually, but the exact definition then follows through the semigroup that it generates. And much as you have the convolution operator in finite dimensional systems, you have something very similar in finite dimensional systems as well. And in fact, if you look at this expression that I've just highlighted, it looks like the one for finite dimensional systems, just with e raised to AT replaced by this function T of T. All right, so that's how, so there we have this analogy. So which means the solutions can look alike, and we can probably do more with this resemblance. Now, in the previous problem, we conveniently ignored the control input that arises in boundary control systems. In fact, in a lot of PDEs, controls do arise as boundary conditions because they're typically point control inputs. So let's look at a boundary PDE, a boundary control PDE now. So here you have a PDE z dot equals az plus some external forcing f, and the control input enters through a boundary condition. And then we have the output of interest as well. Now we're going to make some transformations. We're going to define a new state W given by z minus beta into u. And this operator beta is chosen to satisfy this particular condition. What is interesting is that when you do it, you effectively pull this control input u from the boundary to in line with the differential equation. So it's still in the boundary, of course, but for representation purposes, it's going to come in line with your differential equation, and the resulting equation looks something like this. And now, if you extend the state space now to include the control input u as a state, because you now have u dot featuring in as another control input, you get a form that looks exactly like the PD that we saw earlier. And these PDs are called semilinear PDs. So you have the linear term A, you have classic linear forcing, and you just have this non-linearity acting as a perturbing term to this PDE. So the point being, this kind of a representation that I've highlighted is generic enough for most of our purposes. A lot of our systems can be captured this way, whether the control input enters in line or whether it enters through the boundary. What is interesting additionally is that if you look at this object A now, it might as well be functions of the form A0 that we saw on the previous slide, which operate on functional spaces. And it could also consist of traditional matrices, which means this representation that we have here is generic enough to cover not just PDEs, but also combinations of PDEs and ODEs. And this representation is what we need to represent the dynamics of a system where part of it is functional, it operates on functional spaces, and part of it resides in the standard finite dimensional real space. So we have now a nice little lingua franca. Sorry, I just need to have some water. Okay, so now let's proceed with control design. And we're going to make some assumptions now. We're going to assume that in this particular semilinear system, A and B are both known. And if they're not known, you typically replace it with what is called as a model matching condition. So it really makes no difference there. And we'll assume now that we can write this nonlinear function f in terms of in terms of this linear parametrization. So write it in terms of an expansion. These functions phi are basis functions that depend on x and the state w. X, by the way, is the spatial dimension. And alpha I are assumed to be unknown functions of time. So this is a fairly standard representation. And this is also very conducive to higher order representations. Like, for example, if some of you are interested in neural networks, you would know that this representation is very generic to most neural networks. So, or any other function approximator for that matter, where these PIs are known functions, and you choose to represent f as a linear combination of these functions. All right, now for the moment, we leave alpha I alone as a function of time, but this dependence on time will come into question going forward. But for the most part, it's okay. Now, our control objective here is to stabilize this system. And we want to ensure that the output Y tracks a reference signal R. For the moment, again, everything is in the single input, single output domain, but the state W can be much richer than that. All right. Now, this is just an observation that control laws for PDEs are usually sensitive to the exact form of the PDE. Now, what I mean here is the following. If we were to just look at finite dimensional systems, and let's say we have matrices A and B, then a control law of the form U equals minus KX that stabilizes the system can be typically computed readily for any given A and B. This is true both at a conceptual level in terms of representation, as well as at an algorithmic level. For PDEs, however, that is generally not true, just because PDEs also have a very different structural form from one another. So a control law that stabilizes, let's say, the wave equation will look very different from a control law that stabilizes a beam and one that stabilizes some other PDE. So in terms of representation, they involve different type of derivatives, they involve different terms. So it's not usually possible to just write U equals minus KX and hope that we can compute K easily for PDEs. So with that caveat, what we appreciate also is that if there's a nonlinearity F in this equation, it's going to complicate our representations quite significantly. So there is some merit now in at least staying with control design in the linear domain to the extent possible. Even though we don't have generic representations, we have representations for enough classes of PDEs that maybe, hopefully, we can build a representation for you as long as the PDE is something that has been encountered in the past. All right. So to get into that kind of a mindset, that's what led us to the framework called as a dyadic adaptive control framework. And the idea was as follows. So I have a semilinear system here, and which basically means that if I had to keep my control design in the linear realm, I would have to make sure that my control system on which I design U, does not have F featuring in it. And the best way to do that is to split W into two virtual states. One state is what we call as W homogeneous, or the homogeneous half of the system. And the other half is what we call the particular half. And we do it in such a way that the homogeneous half does not have f in it, and the particular half does not have u featuring anywhere in it. These are virtual states, and therefore my control input u now gets isolated to just one half of the dynamics, which is linear. So let's look at how it's done formally. So we start by stipulating that the control law has this particular form. So it's given by negative k into w. K now is an operator. It's not a matrix of constants because w is a, if you remember, w resides in the functional space. So we have one term kw that's going to stabilize the system, and we have a term v that's going to help us with tracking. And we postulate that this k is chosen so that this term a minus bk generates a stable semigroup. So that's our stabilization condition. Next, we perform this decomposition that I told you about formally, but because the states are virtual, any formal decomposition has to make use of observers. So I now define the homogeneous half of the observer through this state w hat h, and the particular half by the state w hat p. So if you look at this observer, what you will see effectively is that we've injected w ahead of ahead of time. And then we've created the homogeneous half by retaining just the term b into v, which comes from the control signal. And the nonlinearity f has been simply passed into this particular half. And therefore, when I design my tracking signal v, my objective changes to ensuring that the output of this homogeneous half, which is y hat h, tracks the original reference signal r minus the output of the particular half. So this is conceptually very nice because it's simple, but it's also very nice because now for the control design problem, I get to operate on a linear system, namely the homogeneous half. Now there are two complications here. The first is that the fact that I'm going to pass this signal yp hat of t into the reference signal means there'll be some complications going forward. And second, in doing so, I may have to worry about the effects of this yp hat on stabilization, because this yp hat depends on wp hat, which depends on f hat, and therefore depends on w. So this is actually a loop closure of some sort. So we have to take care of it. But anyhow, at least we have a nice representation, and we have what looks like a nice control design problem. So we now have to address three problems. The first is to choose a suitable stabilizing term k. The second is to choose a suitable representation for this signal v, and then to design an adaptive law for f, because f is unknown. So we replace it by its predicted equivalent term. Now, in the simplest setting, because my homogeneous half is a stable system, and I have to track some signal sigma, which is r minus yp hat, I can simply choose to have my control input v look like so. In the Laplace domain, it's just the filtered version of the Laplace transform of r minus yp hat. And this goes through because my homogeneous half is stable. So the question of choosing v in that case comes down to choosing h. So we end up, just to summarize, three problems: choose k, choose h of s, the filter, and choose an adaptive law. All right. So before we go into the details, because this is where most of the math now starts to come in, let me just show you a few results. So conceptually, our block diagram looks like so. We have a system. Its state w passes into the particular half. The output of the particular half is compared with the reference input, passes into the homogeneous half, which effectively acts just like a filter, if you will. The state of this homogeneous half is passed back into the particular half for observation, and the output u is simply passed to the system. So we have this nice, elegant looking block diagram for this system. So let me just show you a few results of how this actually performs in simulation. So we start with the unstable wave equation. It's linearly forced, and this equation is stable in its own right, except it's rendered unstable by the external forcing. So very similar to the Flutter problem that we saw earlier. This time, however, the control input comes at the root instead of the tip, and the output is the same. It's the integral of theta over the spatial domain, which in this case is 0 to 0.1. Now here we design our control law in a slightly different way, in the following form. So we start by designing our observers just as we designed them earlier. So I'm just going to highlight those equations. If you compare it with the parent equation at the top, the observers look exactly like how we designed them earlier, except for one change. When we design U, we've allowed U to sit as is in the boundary condition. We haven't added any stabilizing term yet. So the assumption is that the stabilization term gets added because of these extra terms that you see on the right-hand side of equation 4. The terms that are scaled by P, those are the terms that stabilize the observer, but the expectation is that they will also stabilize the parent system. So when we designed H for this particular system, it looked pretty much, it was a second order filter, if I'm not mistaken. Sorry, we got a response such as the one that's shown here in the plot. So we gave a tracking signal which looked like the combination of a step and a couple of sinusoids. The idea here was to see A, if we could track constant reference signals, if we could track sinusoids, and 2, whether the transient response of the system would be consistent while moving across these. And all these objectives were achieved here. So clearly the technique works well, and it works well even when you don't inject an explicit stabilizing term like we injected previously. So this was one example. We also incidentally tested this experimentally. So I've skipped those results for now. Now let's go down to the problem of choosing K and H. Some of the slides, by the way, might be a bit dense, so I'll just walk you through the slides. And we'll just focus on the key points here. Now, remember, our primary constraint for requirement, if you will, for K and H is the following. A minus BK has to be stable so that we get stable halves. And our HS, now HS initially was chosen for tracking, but HS has a more practical application. In most systems, HS acts as a low pass filter. It actually filters out all of the high frequency signals that might come from anywhere else in the system, either from the control logic itself, in this case from the adaptive laws, or from external sources. So in addition to ensuring tracking, HS must also have a frequency that's sufficiently low to ensure that none of the high frequency signals get into the system. Now, with this combination of K and H, we still run the risk of destabilizing the system because of F. F depends on W, and we've only passed information about F through YP hat. So we have to take some additional care. And that translates into, sorry, an additional condition for stability, which comes from the well-known small gain theorem. So the idea is that in that, if I can just go back a couple of slides, if you will, in this block diagram, when you compute the gain going around this particular loop, the overall gain of the system has to be less than 1. Informally speaking, that's what's going on. So the way we compute the small gain condition is as follows. Sorry. So we define first the Hilbert space on which our functions live. This Hilbert space is Z. It's block Z. It typically involves pair integrable functions, but additional constraints are imposed. For example, the derivatives typically have to be absolutely continuous depending on the order of the PDE. Now, once we define a norm on Z, it's a Hilbert space, so the inner product gives rise to the norm. We look at that norm at different points in time, and we compute the value that's the highest value across all times. And that norm is called as a W norm. And functions where this W norm is bounded give rise to this space W. So this W is a Banach space. Now, what we want to do is to define the small gain theorem in terms of the induced norm from W to W. So what I'm saying is, my system, this actually comes about because my system lives on this, hopefully on this space W, and whatever results is also going to live in the space W. So I'm going to ensure that my induced norm of the system, the loop gain, if you will, from W to W is sufficiently small. And one specific manifestation of that is contained in this box here. Now, this box lists one small gain condition corresponding to one specific type of PDEs. For some classes of these infinite dimensional systems, the small gain condition is extremely simple. It looks like norm of one transfer function and norm of another transfer function is less than 1. However, in this particular case, we have a PDE that depends on W, not PDE, I'm sorry, the nonlinearity F that depends on W, and that's actually what creates this kind of a structure. Now, if you look at this particular equation, the real small gain condition that is generic to all systems is buried in the denominator. And in the denominator, this particular term effectively functions as the loop gain. So that loop gain has to be less than 1. That is a necessary condition. And on top of satisfying that necessary condition, you have to ensure that a constant rho W exists such that this bigger condition is satisfied. Now, what does a bigger condition feature? It features some information about the initial condition rho 0. It features information about the exponential semigroup that we generated through A. These constants, nu2 and nu1, are the Lipschitz constants of the nonlinearity. So there is information about how rapidly the nonlinearity grows with respect to the state buried in these functions. There is something that depends on R, which means that this, although you may not know R ahead of time, you have to be aware of its bounds ahead of time. And there are a few additional constants that are buried in delta 0 u that don't depend on either R or on W. These are constants that are just specific to the system. So it's a function of all of these constants that has to be satisfied as part of the small gain condition. Now, sometimes a small gain condition can be conservative. So if you occasionally in practice, if you violate it by a little bit, it's okay. It's not going to harm you very much. But this has to be typically satisfied through an iterative design cycle. All right, so now we know how to choose K and HS. Now there's one more way to choose to solve for K, and that can be done using the linear quadratic regulator theory. And here the choice of H can be formalized. This is some recent work that we've been doing. It's not closed. It's still a bit open-ended. But here's what we do: we define our cost function as the integral of the tracking error. And the tracking error is represented in terms of yh hat and sigma, which is r minus yp hat. And this is in fact the tracking error that the control signal actually tries to manage. And we have some terms that penalize the magnitude of the control signal. So standard LQR stuff. And for a cost function such as this, it turns out that the tracking solution, that a tracking control law can be written in this particular form. Now, when this time t, which is the horizon of the control problem, is finite, you don't get a tracking control law like this, but we assume that t is much, much bigger than 1, which is it's sufficiently large so that I can write this term R inverse B transpose this pi. This pi comes from a solution of the Riccati equation. It's typically a function of time if that capital T is small, but because it's large, I can replace my Riccati equation by its algebraic equivalent. And so I end up with a time invariant operator K. That's the assumption. And now when you do this, for V, you get an explicit formula given by R inverse B star QT. Now, B star is the equivalent of B transpose in finite dimensional systems. And this is the exact formula that you would have in a typical linear quadratic regulator problem. The only caveat here is that this function Q has to be solved as a boundary value problem. Its terminal value is known as long as T is finite. But the key problem is that it features sigma of T. And sigma of T depends on yp hat of T, whose values are not known a priori. You may assume that R is known for all times. That's okay. But you can't assume that yp hat is known for all times. So this creates a problem with causality that needs to be dealt with. But anyhow, again, we have a representation, and we can still do something with this representation, if only for our educational purposes. So we don't have to worry about h of s, having to construct h of s as we did earlier. That h of s gets constructed directly through this system. What is interesting also is that the system that constructs h of s is in fact a mirror of the closed loop system. So our transfer function h resembles the closed loop transfer function g, if you will. All right. So we have this LQR design. By itself, doesn't look very insightful, but let's see what we get when we make some special assumptions on this particular system. So, we are doing LQR for classic systems on the one hand, and LQR in this dyadic framework on the other. So let's see how they compare. So to generate a comparison that is insightful enough, we start with two assumptions. We assume that the reference signal R is a constant, and we assume that the nonlinearity is non-existent. So we are down to a perfectly linear setting, and for which an exact LQR-based solution is well known. In this setting, it also turns out that for Q of T, which I told you might be difficult to compute ahead of time, there is an explicit formula which is given like so. And because Q of T is now known, albeit in terms of these extra operators, AM inverse and C star, Don't worry about their exact form, but the point is these are known operators. It turns out that you can write a tracking control law precisely without any further approximation or worrying about the causality of obtaining Q. And it turns out that this control signal actually converges exponentially fast to the control signal generated by the traditional LQT law. That is to say, in the parent system, if you didn't do this dyadic decomposition, because the system doesn't have nonlinearities, these two laws converge exponentially fast to each other. This says one additional thing, that even in the simpler setting, the two laws are not identical, which means the cost functions will differ. However, exponentially they converge to each other, which means that there is hope that we can prove suboptimality in a guaranteed sort of way. So, that's one property. The other thing we also looked at was to see if we could now derive h of s formally when these simplifications don't actually work. So now this h of s is a transfer function. It can be realized in terms of a state space system HA, HP, and HC. And HA is a stable system. Now it turns out that technically, I wouldn't call it an exact solution, but a technically optimum solution, if you will, actually is found by solving another problem, which is listed out here. It says find X such that this particular condition is met. Now here, let me tell you a little bit about what these terms are. GM is the transfer function of our closed loop system featuring just A, M, B, and C. That's if you will the homogeneous half. GM star is its adjoint operator. So and this particular adjoint operator may not be perfectly causal. So what we are saying is we want to find an X. This X has to lie in H infinity, which means it's a causal operator. So we want to find the closest causal operator to this GM star. And that's our solution for H of S. And because we also want to achieve tracking, the fact that H of S chosen randomly won't give you tracking, you impose an additional condition that's written out here. For those of you who've taken classical control, you'll know that this is the DC gain condition, that the closed loop DC gain has to be 1 to guarantee tracking. Now, if you omit this condition, what remains is a well-known problem called as a Nehari problem. And there is a computational way to solve that problem. When you add this condition, this problem, as far as I know, is not a solved problem. So the point is, if you can solve this problem, then you can solve the problem of determining H in an optimal sort of sense. And any H that satisfies this particular condition also guarantees some sort of suboptimality with respect to the cost function. All right. So very insightful. So let's move on now. So as I told you, we were supposed to design 3 things: K, H, and an adaptive law for F. So K and H are now done. Let's look at the adaptive laws F. So let's start by recollecting the expressions for the homogeneous and the particular halves. They look like so. Now, if you remember, the nonlinearity F was written as in terms of this linear parameterized form, where phi was the functions phi are assumed to be known, alphas were unknown. So when we predict F, it suffices to predict alpha. So the predicted value of alpha is written here as alpha hat. So with this expression, we can now write the dynamics of the observer error, which is denoted here by W delta. It's W hat P plus W hat H minus W. So it's the observer error for the complete observer. You get a system that looks like so. So you have a stable part of the system and other perturbation terms that we would ideally like to suppress in some way. Now, if alpha were known, I could set alpha hat I equal to alpha, and then this term would go away. Likewise, it turns out that under very special circumstances, it's possible to design alpha hat so that it converges to alpha. It's called as a persistence of excitation condition. And even in that case, this term can be made to go away. But fundamentally, I have to still design some kind of a law for alpha hat and then impose things like persistence of excitation on top of it. So the most fundamental law that is now used is called as a projection-based law, and it looks like so, representation wise. So alpha hat dot, so it prescribes a dynamical equation for alpha hat. It looks like projection of alpha hat onto some other object. Now, what the projection does here is as follows. When alpha hat is inside the acceptable bounds on alpha hat, this projection operator simply equates these two terms. So alpha hat looks exactly like this term that's shown here. And I'll tell you how to interpret that term in a minute. But when alpha hat starts getting close to its acceptable boundary, its derivative starts to reduce and eventually settles down to 0 and thereby prevents the boundary from being crossed. So in that way, this particular law keeps alpha hat within acceptable bounds and thereby prevents the system from being destabilized. This term gamma is called as the adaptation rate. We'll have a little more to say about it in a minute. This term here represents the inner product, or if you will, the transpose in an abstract sense of these two vectors. So Fw is just F, you've already seen it before. P is a solution to a Lyapunov equation featuring AM. So as in the finite dimensional case, we can find a Lyapunov function P for this system AM under some circumstances. And I'll have a little more to say about this going forward. So if this P can be found, I can write this inner product and I can compute alpha hat directly, and then I'm done. So let's see what happens next. So to understand the role of that Lyapunov equation, we have to start by constructing the Lyapunov function, which I've shown in equation 12 here. Once you differentiate it, you can show that v dot is less than equal to this term on the right hand side. I've also assumed, by the way, that alpha of t is a constant and alpha, because there's a little more insight to be gleaned from it. If alpha is not a constant, there'll be a few additional terms here, but those terms are bounded. So a lot of your guarantees will still go through pretty much as is. Now, we make one assumption here, namely that P is coercive. What we mean by coercive is that, in effect, this term Z transpose PZ is bounded below by some term of this form. C1Z, and sorry, there should have been a square here. I've omitted the square. Now, this condition is trivially satisfied in finite dimensional systems. If P is a positive definite matrix, then this condition trivially holds. It turns out that in infinite dimensional systems, that is not the case. So we have to worry about the fact that P may not be coercive. In any case, when P is coercive, we get a very strong bound on W tilde. What I mean by a strong bound is that it tells us that W tilde for all times is bounded above by some such set of numbers which can be made to shrink to 0 by ramping up gamma. So the faster you learn, the tighter the bounds get on the observation error. But these bounds go through only when P is coercive. In finite dimensional systems, that's not a problem. But in infinite dimensional systems, such a coercive P need not exist. So that's the last bit I want to talk about now. So as a simple example, if you look at the heat equation, the unforced heat equation, Wt equals Wxx, what you can show is that for a bounded Q, Q being the right-hand side of the Lyapunov equation, you cannot find a bounded P. A coercive P. So the way to make it work in the case of heat equation is to simply set P equals the identity operator. And so that Q can now exactly equal A. It turns out A here is the same operator that we saw earlier. It's a double differentiator. And it turns out that in this particular case, it generates an exponentially stable semigroup. And therefore, this particular scheme goes through. But it doesn't go through all the time. Now, why is this important to us? Well, other than just getting mathematical guarantees, in our scheme, if you remember, the tracking error y minus r is written in this particular form because we design yh hat so that it can track r minus yp hat. That's the control objective. But that leaves y tilde out. So if your y tilde can be made small, your tracking error can be reduced and made arbitrarily small. But if you can't guarantee bounds on y tilde, it's difficult to guarantee bounds on the tracking error. So that's the problem that we end up having to encounter.
Aditya, you have 1 minute.
Sorry?
Just 1 minute left.
Yeah. So we've actually got two recent results here. So I'm going to run you through them. But basically it says the following. For two classes of systems, for one class, if this kind of a KYP lemma can be met, you can show that y tilde still satisfies the same strong bounds that we obtained earlier. So tracking error is really very well behaved. Unfortunately, you can't say the same about W tilde, which is the observation error. And what that means is that the two signals will converge, but you can't guarantee how bad the transients are in the process. I mean, these will converge really, really fast. That's what we are saying. But this happens in a very special case of circumstances. More generically, and that's, I think, a more generic result that we've obtained recently, and this only works when this alpha is a constant and not a function of time. You can actually show that y tilde converges to 0 asymptotically. But similar guarantees on W cannot be provided. So you can show that a tracking error will converge to 0 eventually, but the transient response cannot be controlled. Now, this in DAC, this might be acceptable, but when you go to model difference adaptive control, the implications are fairly serious because the same Lyapunov analysis that I just showed you is actually used to prove stability of the system as well. So what we're saying is you can control the asymptotic behavior of the two systems under these weak conditions when there is no coercivity, but you have absolutely no transient guarantees on the tracking signal. So this is an implication that's very localized to PDEs. So just to conclude the talk, we saw two different architectures for infinite dimensional systems. First, we saw systems with a finite relative degree, where you saw how output feedback improves stability margins in a guaranteed sort of way, despite acting on a single dimension. And we then saw a dyadic adaptive control architecture for PDEs. We had the architecture, but the two takeaways, I think, are how LQR operates in the infinite dimensional systems and how the lack of coercivity of the Lyapunov operator impacts the tracking guarantees. And this feature is especially, again, localized to infinite dimensional systems. In finite dimensional systems, it's rarely a problem. So I think with that, that's the end of my presentation. So thank you very much for your attention. Does anybody have